Hi everyone. Today we are going to go over how to constrain beam stresses for MSC Nastran Optimization. As always, if you have any questions, if you want more advanced training, if you want me to work with you on an optimization project of your own, if you want access to the web app we use today, you can contact me at this email address and I'll definitely get back to you. So today, again, let me describe what our model is, and then I'll go over what our optimization problem statement is, and then I'll walk you step by step on how to construct your beam stress constraint for this model. Currently, we have a beam that's fixed on one end. There's a moment applied at the other end. It has this stress distribution through the cross section. We currently have a maximum beam stress of 4.95 megapascals at point E. Here's what our model looks like. It's a simple model composed of line elements, again, fixed on one end. A moment of 12 kilonewton meters is applied at the very tip. Here's where the cross section looks like when it's superimposed. Our original cross section has dimensions of 0.4 meters for the height and 0.2 meters for the width. And now for our optimization problem statement. We are minimizing the weight of this beam as much as possible. We are going to let the dimensions of the cross section vary so the width and height can change throughout the optimization process. But what we want to do is at the very tip of the beam at point E, we want to make sure that the stress or the bending stress is no more than 6 megapascals. So again, our current stress at point E at the tip is 4.9 megapascals. Our constraint is 6 megapascals. So this gives us a little bit of flexibility in augmenting the cross sections, so we can change this until we have a beam stress of 6 megapascals. So let's go ahead and jump into Patron and show you what our current state of the model is. Here I have the line elements superimposed with the beam cross section. Our current beam stress at point E is at a value of 4.9 megapascals. So let's go ahead and take our web app and construct our constraint. And let me make sure I go to the right directory. Here, once you're in the web app, click on constraints and filter down until you find stress. You'll find multiple options for stress. There's a stress for composites if you're working with that. There's a beam stress for PBR sect or PBM sect. This row is for cross sections that are arbitrary. If you're using a beam cross section that's in the library, you would just use the normal stress constraint. This is what we'll be using today. So click on the plus icon to create your one stress constraint. In the property type in ELEM. Here where we're saying we want to constrain element 10. Element 10 is this final element that you see at the very top. Let me turn off the beam cross sections actually. And here if I put on the ID numbers, element 10 is this very top element. Let me go back to the web app and type in our upper limit of 6,000 or 6 megapascals. So 6E6. Here it's very important you include the decimal point. Here I'll type in 6.0 E6. This is my upper constraint of 6 megapascals. And now for item code. We need to know the element name for this element. Here we are using C-bar elements. And so for our Nastran quick reference guide, go to chapter 6, table 6.1. You'll find a section called element stress item codes. Go down the list until you find C-bar elements, and here you'll find multiple C-bar options. C-bar for intermediate stations and arbitrary cross-section. The one we are using today is linear, so we're using C-bar 34. Look down the list and look for end B point E. And now let me describe the difference between end A and end B. each element here has an end A and end B. Let's go ahead and plot the element coordinate system for element 10. So that would be this. So element 10 has a point A, which is the starting point of the element, and a point B, which is the ending point of the element. The ending point happens to be the end of the entire cantilever beam. So hence, I want to use end B, point E. If we look back at our item codes, we see that there are item codes for end A, or the starting of the element, and end B, which is the end point of the element. I find my end B item codes. I want to monitor the beam stress at point E, so we'll use item code 12. Let me minimize this and go back to my web app. I'll type in 12 here. In the right are my new output statements, or Nastran statements, that I then need to use in my bulk data file. My bulk data file already has statements for the design variables and the objective, and I've just pasted my new statements for the design constraint. So let's go ahead and now run our optimization. And now what I'll do is I'll close some of these applications. The reason I'm closing these applications is I'm running a virtual machine, and I want to make sure that there is enough memory for this optimization. I'm already running on a small amount of memory, so I just want to make sure there's enough memory for the optimization. Once that is complete, open the F06 file, inspect the very bottom to make sure it says run terminated due to hard conversions at an optimum. And here we see that successful message. And now let's discuss our results. We started at a cross section where the height was 0.4 meters and the width was 0.2 meters. And just bear with me while PowerPoint is starting up. And the way we can tell what our difference was in the design variables, here, as I highlighted, are the original values for the cross section. At the end, we have the final cross section values of 0.28 and 0.227. So let me actually close PowerPoint and restart it. I might have to use PowerPoint for this. And as mentioned at the very beginning, the beam stress at point E of the cross section was still within the limit. So here, let's finally jump to my results. Here we started with the mass of 644 kilograms and we ended at a mass of 524 kilograms. So this is great. The mass of the beam was reduced. Here is our original cross section. Here's our final cross section here on the right. As I mentioned, the 0.29 and 0.23 are referenced from the F06 file, where the values are listed in the last design cycle that you see me highlight here with the mouse cursor. Now, as for beam stress distribution, again, the beam stress at the beginning at point A, E, was 4.95 megapascals, but at the end, it is now 6 megapascals, and the new values of the other points are listed here. Let's go ahead and view these results in Patran. What I'll do is I'll attach the results that were provided during the optimization. And then I'll go ahead and superimpose the original beam stress for point E. So again, we started at 4.9 megapascals. And now let's look at the stress at the last design cycle for point E. And then here we see it's 6 megapascals. And let me show you what the stress looks like for point F. At point D. At point D, we should have a stress of negative 1.85 megapascals. So point D, and that's what we have, negative 1.85 megapascals for point D. So now, this was the process for constraining one element. How do we constrain multiple elements? What we can do is we can type each element individually, so element 9, 8, 7, and so on and so on. But this becomes very tedious. What we can do is now use the property method of constraining beam stresses. If we know the property type, which here we use PBARL, and all the elements are using this PBRL, so element 1, all of these ones are pointing to this PBARL, I can now say this constraint is applying to any element associated with PBARL1. So now the constraint is applied to every element associated with that property type. And it gets even better, because if I then had a larger model with more PBARLs, I can then say use property ID 1, 2, 3, 4, 5, whatever the property ID is, you can type it in here, and then the constraint will be applied to every element associated with these property IDs. With that, this is close to the end of my tutorial. Again, I provide a wealth of additional optimization training for size optimization with MSC Nastran. If you want my guidance on a project of your own, if you want access to my web app today that makes it really easy to create your constraints, you can contact me here at this email address and I'll definitely get back to you. With that, thank you so much for watching.